It is a subject that has to do with convex geometry, and the title is a little bit catchy because occasionally I give this lecture also in high schools, and then the students are more attracted than when I say convex sets or something. Well, what I really want to talk about is convex sets of constant width. Now, what is the width of an object? If you put it between two parallel lines, and you measure the distance of these parallel lines, you can measure the width, for instance, of a screw or of a bolt. Yes. And here you see a building that does not have a circular shape, that sits on the other side of the River Rhine across the Cologne Cathedral. And people were upset because those people that lived behind this building, they could no longer see the cathedral. And they were wondering if there was maybe by turning this building, rotating it a little bit, it is easier. You see more of the cathedral. But in fact, this tower has a cross-section which is a set of constant width. And when you go up on the tower, you can take an elevator up, and so the light does not work. On the top floor, you can look across the river. And you see the Cologne Cathedral, and Cologne is relatively flat and much smaller than St. Petersburg, 1 million people only. So, and the name of this building, the German name of this building is called Cologne Triangle. Yes. And are there other towers that have this property, that they have constant width no matter from which side you look at them? And there is an animation that tells you, yes, there are. Let us look at this set. This set has 5 corners. And if we put it inside a square and rotate it, it touches always all 4 sides of the square. So this is a convex set that has constant width. The one that we just saw, this tower, has only 3 corners. And this sort of rounded triangle has a particular name in mathematics. It's called the Volo triangle. I will tell you a little bit more about Volo later. Notice, as this triangle passes through the square, it covers almost entirely the inside of the square. And this observation can be used to build a drill that drills square holes. Now, if you don't like the fact that it has corners, you can put something around it. Now the boundary is of class C1. And it is still a set of constant width. Because in every direction you have added a certain width. And you can do this with any odd number of corners. So in Cologne, some young people drive cars which have wheels like this. When they go past you, it goes boom, 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 boom. Okay, so there are many sets of constant width. And in fact, one can give a mathematical definition. Any convex set can be described by its support function. The support function measures the distance from some origin that a tangent plane has under a certain angle theta. And here we see this plane and we see that plane, and the angle theta has turned by p, and p of theta plus p of theta plus p should be equal to d, the constant width of this set. So any function p that has this property describes a convex set of constant width, and there are many functions. For instance, p equal to d over 2, the constant d over 2. But you can add a trigonometric function to it, and you can add a Fourier series, and it still satisfies this kind of equation. Now, these are all sets of constant width. They are buttons, and there is a saying, there's a little legend or anecdote that the wife of Rollo was an engineer, that the wife of Rollo said he was always inventing things that she did not find useful. He should invent a button that cannot roll away. And he said, well, the perfect button has to fit through the buttonhole with epsilon space in between, no matter which way you turn it. And that's why we have circular buttonholes. Well, we have circular buttons. But these buttons also have constant width. We can pass them around. Yes. It was not easy to find them, but they exist. Right. Now here let me construct the sets of constant width that we have seen so far were invariant under some finite rotation. Here we construct a set which is invariant under reflection. And since the light doesn't work, oops. No. Maybe I can do it like this. So I have here a triangle. The longest side has length d, the other two sides are equal. And then I put a circle in here and rotate it until I get to the extension of this line. And I do the same over here. And then I rotate this stick around the point in the middle. And I get the upper circular arc and the lower circular arc. In this way I can construct a two-dimensional set of constant width. And this set has no two-dimensional rotational symmetry. Now when you rotate this set about this vertical axis into 3 dimensions, you get a 3-dimensional set of constant width. So this set has in common with the ball the property that you put it between 2 planes, and no matter which way you roll it around, the 2 planes always have the same distance from each other. Here's this is the rotated version of this body. Also, coins are not always circular. We have coins. They're used mostly in Great Britain and in places where the British Crown has ruled. This is a 50-pence piece. It has 7 corners. And although it is not perfectly round, you can use it in automats, in vending machines. The coin does not get stuck when it falls down, and it does not have too much slack. So this is a 2-dimensional set of constant width. And one may ask, why does one have these coins with corners? And this is due to the fact that you do not need so much material for those coins. First, let me state a theorem that is relatively old, by Barbier. It says all convex plane sets of constant width have the same diameter. Same diameter as the disk, and that's p times the diameter. And so if I have different plane sets of constant width d, they are all isoparametric. They all have the same perimeter. And there's the isoparametric inequality that says among all isoparametric sets, the disk has maximal area. Therefore, for a gold coin that has a given diameter, you need more material than for a coin that has corners. Now, as a mathematician, the next natural question is, and here's a proof of this theorem of Barbier. The perimeter can be expressed in terms of an integral over the support function, and you integrate the support function only from 0 to p, and you shift the argument. Then you have integrated it from 0 to 2p. You add those two, and you have the functional equation that says the sum of these two is constant d. Therefore, this is the theorem of Barbier. Now, which coins require the least amount of gold? Silver coins, maybe, but there is a theorem that says among all plane convex sets of constant width, the Rollo triangle minimizes area. And this is a non-trivial theorem. This is, there are many different proofs. The first ones were given by Blaschke and Lebesgue, and in fact this is known as the Blaschke-Lebesgue theorem. And it's interesting how Lebesgue came up with the proof, because Lebesgue was asked about Buffon. No, he wanted to study a version of the Buffon needle problem. The Buffon needle problem says when you throw a needle on the floor, on a parquet floor, and the distance between two boards is the diameter, what is the probability that a needle falls across a line, it falls on two different boards simultaneously. And after that problem was understood, people said, what if we take another shape instead of a straight line that has length d? We take something like an eel. That is, I don't know, you know the Russian word for eel? It's a fish that lives in the sea and in the rivers. It looks like a snake. Yeah? Oh, okay. So this problem is also known as the Buffon noodle problem, as opposed to the Buffon needle problem. And Lebesgue said, I cannot answer this problem, but I can answer it if I have a fish that looks a little bit like a flounder, and a flat fish. And so he got interested in these Rollo triangles. That's how he found the proof. Now, in terms of calculus of variations, I mean, okay, this is a classical minimum problem. To calculate minimum area under some side constraint is an easy exercise that we have all done in high school and so on. But here the side constraints are tricky. And in fact, if you want to write it down in terms of a variational problem, what you're trying to minimize is a combination of the support function and its derivative. And this functional here is non-convex in P prime. So minimizing non-convex functionals is not so trivial. And secondly, when you minimize, when you do variations, you always have to keep in mind there is a convexity constraint and there is this constant width constraint. So you cannot do local perturbations of the boundary and derive something that says, oh, the boundary must have constant curvature or something like that. In fact, it doesn't, because the curvature jumps here. Now here we see a Rollo triangle and a disk, one on top of each other. We know the disk has maximum area, the Rollo triangle has minimum area. What is the difference in area? What order of magnitude would you guess? 50%? Is 12%. It's about 12%. So if you are in some restaurant and they bring you a plate like this that is filled, yeah, they're trying to cheat you a little bit. Yes. So. The Rollo triangle, of course, is a fairly old pattern. You find it, for instance, in Gothic cathedrals. Here we see it. Up here, there's one there. And then you see many of those. So there's one here, and one there, and one there. Now, who was Rollo? Rollo lived, well, not in the last, but second last century. And he was born near Cologne. And there were 7 children. He died, his father died when he was 3 years old, and then he moved to an uncle in Koblenz. and he studied mechanical engineering. One of his teachers was also the teacher of Skoda, who built cars later. And later he studied also philosophy and science in Berlin. At the age of 27, he became professor at the Polytechnicum in Zurich, which is now the ETH in Zurich. And when he turned 35, he became director of some academy in Berlin, which is now the Technical University of Berlin. And he was an interesting character. He was an art dealer. He sold paintings to the German emperor. And he collected animal specimens because he was interested in how joints are working, and he wanted to build better machines that could perform odd movements. He also built mechanical models so that the students could practice with them and could really touch them. And he was an advisor to Otto, the inventor of the four-stroke engine, and Werner von Siemens. He helped to found the German National Patent Office and so on. And these are two typical citations of him. The first one says, "The thorough understanding of old mechanisms is more important than the design of new ones." So first do your homework somehow. Yes. And the second one comes from an interview that they made. Rollo was often on committees that were giving prizes on world exhibitions. And once he was in Chicago and he was interviewed how the German products compare to the American products. And he said, well, the German products are poor and cheap. So in those days, this got him into a lot of trouble. But what he also said was that under economic competition, improving the quality of a product is more important than lowering the price. And it seems that in the end, part of German industry has taken his advice. This is a monument that was built 5 years after his death. So it is about 5 meters tall. In the middle you see a bust of Rollo, and it says here, to Rollo, the teacher and inventor. And this is a steel worker with a leather apron. Yes. And this is somebody who just came from a mountain with the laws of nature written on a stone table or something like that. These two figures do no longer exist. They were melted down during World War II. But this is what it looks like today, and it is still behind the main building of the Technical University in Berlin. Now, as I said, Rollo built little machines, and these Rollo triangles are used to build some gears that transform a rotational movement into a piecewise translation. So it goes in one direction, then it stops for a while, then it goes in the other direction. And you need that, for instance, in bottling plants. You grab the bottles, you move them over, then you let them go again. Then you move back. How does one do this mechanically? And the basic ingredient is this little machine that Rollo built. This is how it works. You turn the crank, and then this metal frame is pushed in both directions and sits still for a while at the end. Now, Rollo built whole collections of such little gears. Here is a catalog of his collections. This was a collection of about 250 pieces. And he sold these collections to Tokyo, to the United States. One was also allegedly sold to St. Petersburg. And of course it was in different German universities and so on. And these pictures here and the little video that you just saw are from Cornell University. About 10 years ago, some mechanical engineer at Cornell University discovered all these toys in the institute under the roof, and he polished them and tried to find out what they were meant for. So the one that we just saw is, I think, this one here in the catalog. Now, I said with a Rollo triangle one can drill square holes, and these drills are still being sold by a company that goes back to the Watts brothers, the inventors of the steam engine. And they are very expensive to buy. And let us see an animation to understand how they work. So here we see the construction of the Volo triangle. The center of the Volo triangle rotates along this almost invisible yellow line. And when it rotates, it covers, and this arc of line is similar to this one here. And only, I think, 2% of the square are not cut out. But that is good enough for industrial purposes. Now you have to tell the drill where the corners are supposed to go, and you have to give it some sharp teeth. And you have to allow it to wiggle around inside the square. So this mechanism is the secret somehow, yes. So there you can download the video, yes. Let's see. This is how this looks like when you buy it as hardware. Here we see one of these drills in a lathe. A lathe is a horizontal drill, and on a lathe the workpiece is rotating and the drill is stationary. And here it is sitting inside a guide, and the workpiece is behind it. And this is some Frenchmen at home with children in the background. So this doesn't. So the drill does not rotate; only the workpiece rotates. And then they take off the guide, and up there in the left corner you are supposed to see a square hole. So this works, and it has been used on an industrial scale. Yeah, the Volo triangle is also still in use in rotary engines and in movie projectors. And let's see how these work. So by the way, here we see again a little bit about construction of sets of constant width. One with 7 corners. This is an irregular set of constant width, and one of my students wrote a master's thesis on this construction, describing it and why it works. So one has to think a little bit about it, but it gives you a set of constant width. Now this is Barbier's theorem illustrated, because the length of the chord is not changed when moving from one to the other. And now we see a car with a rotary engines. A friend of mine still has such a car, and he's quite happy with it. And the idea of the rotary engine is the following. In a conventional engine, you use a lot of energy to move a piston in one direction, then the piston stops and you move it down again. If you have a piston that keeps going in only one direction, maybe you can save energy. And this is what happens in the rotary engine. So you have an injection of the fuel, then it is compressed, then it is ignited, and then it goes out. And these engines are machines that you can build in the millimeter size, and they are being used for micro machines, and also they have in the meter size. So there are turbines for gas pipelines where these Volo triangles have 1 meter in diameter. They are still also being used in drones and in reconnaissance planes, because this engine, since it does not move back and forth, does not generate so many vibrations. It's a very quiet engine and very stable. The efficiency of the engine is not as big as one had hoped for. One reason was that when it was invented, people were not able to cut Volo triangles so sharply. Second one is the corners rub off easily, and then because they are exposed to a lot of pressure. Another reason is that the ignition chamber has has not a favorable shape, and so on and so on. So that's why this engine never became so popular. Okay. And in conventional film projectors, the Volo triangle is also used, because when you see a film, you see a very fast show of stationary pictures. And how do you transport a film so that it stops, and then it moves again, and it stops? Yes, and this is done with the Volo triangle. Used to be done with the Volo triangle. Of course, now we have digital videos and so on. I think there's no Volo triangle in my computer. To show you this movie. Okay, so. So these Volo engines are also used, for instance, here is a patent for one that has the size of a cigarette box. And it is, in some cars, when the airbag goes off and you happen to bend forward, the airbag can kill you by breaking your neck. So it is important that before the airbag goes off, your seat pulls you back into your seatbelt pulls you back into your seat. And this is done with such a little engine. There is a gas cartridge, and it is ignited, and then this starts spinning and pulls the seat belt tight, and then if fractions of a second later the airbag goes off. This person, Francis Moon, is the mechanical engineer who found the collection of Volo's instruments in and who made them public. And he wrote a book comparing Volo with Leonardo da Vinci, and University of Karlsruhe was so happy about it that they gave him an honorary degree for making one of their former students more famous. Now there are also three-dimensional bodies of constant width, and this is one of them, a rotated, rounded Volo triangle. This picture is somewhat unusual because it is taken from a book that appeared simultaneously in East and West Germany, in the German Democratic Republic and in the Federal Republic of Germany in 1986. In those days, it was very difficult to communicate between East and West Germany, and this was an exception. Here we see a a genuinely three-dimensional body that does not have rotational symmetry. In fact, it looks a little bit like a rounded off tetrahedron, and it has a name. It's called a Meissner body, and I had it manufactured, and we can pass it around. And this is the oldest picture that I could find, the oldest photo of this Meissner body, and I found it in the book of Hilbert and Cohn-Vossen on. Do you know the Russian title of the book, Alexander? In German it was Anschauliche Geometrie, in English Geometry and the Imagination. Yeah, okay. So most people know who Hilbert was. Cohn-Vossen is not so well known, even though this book is well known. Cohn-Vossen started his career in Göttingen as a postdoc with Courant. And then he had a position in Cologne University, where I am from. In 1932, he gave his first official lecture that was publicly announced on convex surfaces. And then in April 1933, 6 weeks after the Nazis came to power, he was suspended from teaching because he was Jewish, and in September he was then permanently suspended. So there was no way for him to work in Germany any longer, and he went first to Switzerland, where his parents-in-law lived, and tried from there to emigrate to various countries. He was good friends with Hopf, and Hopf knew Alexandrov, the topologist from St. Petersburg. And so he came to Leningrad, first to Leningrad, and then later he moved to Moscow. And he died 1936, when he was 34 years old. Now this is painful to remember. I mean, the Germans have done a lot of cruel things in those days, as you know. But one should never forget what civilized nations are capable of. This picture that we see here is actually taken from his personnel file at Cologne University. Here's another version of the picture that appeared after his death. So. And in Cologne, we dedicated a seminar room to the memory of Cohn-Vossen not too long ago. And there is the dedication table. And some colleague from abroad and somebody from Cologne, yes. So. Now, how is this Meissner body constructed? You start similar to the Rollo triangle. The Rollo triangle you can construct by taking the corners of an equilateral triangle as centers of 3 disks, and then you take the intersection of 3 disks. And here we take a regular tetrahedron and take the intersection of 4 balls. And then we get something that is called Rollo tetrahedron, but that is not a body of constant width. But it is an appealing body. I mean, it was used, for instance, as an icon for some center for Numidia. And when I talk in Cologne about bodies of constant width and mention that the body of Meissner has constant width, people always smile because we have a cardinal by the name of Meissner in Cologne. But it's not this cardinal. It is somebody, Ernst Meissner. Ernst Meissner was a student of Hurwitz, and he had the same mathematics teacher in high school as Albert Einstein. And he talks very positively about his math teacher. He says, this teacher took us serious somehow. And he treated us like real people. Anyway. So better pictures of Meissner's body you can find on the internet. And there you find this one, this one. Now, as you will see, the Meissner body has not 6 sharp edges as the intersection of 3 balls would have, but 3 of the edges are rounded off. In the left picture, the 3 edges meet in a corner on top. The rounded edges. In the right picture, the rounded edges meet on a triangle in the bottom. And these bodies are suspected to have minimal volume. Now there's an old theorem of Blaschke, 100 years old, that says among all 3-dimensional bodies of given width, the ball maximizes volume and surface area, and different sets have different surface area, even though they have the same width. So this is a difference between the 2- and 3-dimensional situation. And the one that minimizes volume also minimizes surface area. In fact, Blaschke gives a formula how they are related to each other. And it's natural to ask, well, what is the body that minimizes volume, given the width, or that minimizes the surface area? And this body is supposed to be Meissner's body, and the first time that this was written down as a conjecture is in the book of Bonnesen and Fenchel. But the conjecture, I think, has been around earlier than that. There's a related result that says, suppose I have 3-dimensional bodies of constant width, but I restrict myself to the class of bodies that have a rotational symmetry. Which one has minimal volume? And that is the rotated Volo triangle. So the smallest 2-dimensional set happens to have a reflection symmetry. When we rotate it around its axis, then it gives a small 3-dimensional set. And this has been proven only 9 years ago. Now here's a construction that was given by Lachon-Robert and Houdet in 2006, and it looks a bit confusing, but it's not so complicated. So I start with an n-1 dimensional body of constant width. So this is an n-1 dimensional body of constant width, an interval in 1 dimension. And then I take anything in the extra dimension that is above, I call E plus, and the other one I call E minus, and the points down here. Now, I construct, I take, okay, now I want to have a 2-dimensional set of constant width, so I add a few points here. And since sets of constant width are always convex, I take their convex hull, and I call this set Q. So the 2-dimensional one should contain Q, and now I take a ball of this radius, and this center, and a ball of this radius and that center, and so on. And I construct the set K plus, this upper part here, yes. And then I take all the points that have distance d from points on K plus, and that are in the lower half plane, and I call that K minus, and the union of K plus and K minus is then an n-dimensional body of constant width. This is what they proved. And it is interesting to look at some special cases. For instance, suppose we want to construct a small 2-dimensional set of constant width, a small area. Then we make the set Q as small as we can, because large Q maybe generates a large set of constant width. So in the first step, what we get is a circular arc here and a circular arc there. And in the second step, we get a circular arc there. We get the Volo triangle. Similarly, in passing from 2 to 3 dimensions, we can imagine that we have a Volo triangle, which is a small 2-dimensional set, the smallest that we know, and the smallest that exists. We imagine the Volo triangle lying horizontally here. And then we do not add any points to form a three-dimensional set. Instead, we look sort of at the dome that we get, and now I need the Meissner body again to show it to you. Thank you. Oops. So we have the, this is the wrong one. So we get something that has three corners, three sharp edges on top. And then we add something at the bottom. And we get the Meissner body. So this is an indication that since the Rollo triangle and the Meissner body are sort of constructed in a heuristically reasonable way to get sets of minimal area and volume, that maybe the Meissner body has minimal volume. Now this mechanism is also good to construct three-dimensional sets in a stochastic way. You take any two-dimensional set as a starting point, and from that you add by stochastically a few points below to form the set Q, and then you construct a three-dimensional set. And I had one student who did this for 1 million different bodies, and I said, well, if you're lucky, maybe you find a body that has a smaller volume than the Meissner body. But he was not lucky. So the chances are that the Meissner body really is the one that has minimal volume. Now, one can also look at this from a variational point of view, and you can ask yourself, well, can we find necessary conditions if we have minimal volume? And yes, one can. One can find out that bodies that have minimal volume, they must have irregular boundaries, in the sense that if I squeeze them between two planes, at least one of the points of tangency is not a point where the boundary is of class C1. And of course, Meissner body satisfies these conditions. Again, that supports the conjecture, but it doesn't prove it. It has also been conjectured, more or less out of philosophical reasons, that the body of minimal volume should have the full symmetry of the tetrahedron. But at least if you take the two Meissner bodies and you sort of merge one of them into the other, you take the body halfway between, where so here some edges are sharp and some are round, here the other edges are sharp and round, and here all edges have the same amount of roundness. You can show that this volume and that volume is the same, but this body that is more symmetric has a slightly higher volume. And finally, there is a result by two differential geometers that say, well, if we have a volume minimizing body, then any smooth part of this boundary has its smaller principal curvature as 1 over the width of the body. And again, if you are on a part of a spherical surface here, the width, the curvature is 1 over d, and if you are on this rounded edge, this curvature is again 1 over d. So this supports it again. And the last result that supports the conjecture is a result by two Chinese mathematicians, which says more or less that Meissner's body are more slender than others of constant width because they minimize the in radius and maximize the circumradius, and therefore they maximize something called the Minkowski asymmetry index of circumradius over in radius. And slender bodies tend to have smaller volume, as we know from everyday life. Yes. Okay. So now we know that there are these strange convex sets, and what are they good for? Yes. Well, they are good to build some exotic drills. and machines. And I want to give you one more example, and that is the Challenger disaster, 1986, so that's already 30 years ago. The younger ones among you will not remember it, but the older ones will remember that during the start of a space shuttle, the rocket exploded. And this was a great shock to the American Space Agency, and they had a big committee to investigate the cause of this accident, and one of the people in the committee was Richard Feynman. And he wrote a little book about it, and in this book he describes, for instance, the problems with bureaucracy that he had to get his hotel reimbursed and things like that, but of course also other things. Now, what happened? So this classical space shuttle, it has a big main rocket, and next to it are two booster rockets. The booster rockets are supposed to give extra boost in the initial phase of the start. And then after the first phase of the start, the booster rockets fall off into the Atlantic, and they are picked up by divers and taken back to the land. They are taken apart, they are cleaned, they are put together again, and they are used for the next start. And something was wrong with one of these booster rockets, because there was some propellant leaking out on the side, and it was burning. And it was burning against the main rocket. And this was not supposed to happen. And then the main rocket exploded. So the booster rocket, of course, is a long pipe, and it consists of different segments, circular segments, and they are taken apart, they are cleaned and so on, and something was wrong with the connection between these segments. In fact, there were some bolts, some screws that were holding the different parts together, and there was something called an O-ring in between. An O-ring is something like this. So it's a rubber ring, yes? And during start, there's a lot of pressure on this rocket, so the material is working, and maybe this gap opens a little bit, but since there is the rubber ring in there, there were even two rubber rings in there, nothing could happen. That's what they thought, yes? And so Feynman took some of this material from the rubber ring, and one of the reasons for the accident was that during this particular start, it was very cold outside, and the rubber ring was frozen, and therefore it was not so elastic. And to show that it is not so elastic, Feynman held it in a glass of ice water. Well, first he showed how elastic it was, and he held it in a glass of ice water, then he took it out and it snapped. This is some experiment that any journalist can understand, and so this was reported as the main accident.
I heard that he put it into his cocktail at the party and showed.
Well, he did also at a press conference, yeah. And but there was another accident that one can find in the official report on this accident, and this is called lack of roundness. So Feynman asked the mechanics, if you reassemble these different parts of the rocket, how do you know that the shape of this pipe is perfectly circular? And they said, well, we have our guidelines, and it says measure the diameter from 6 different directions, and if it is within tolerance, then it is okay. And he said, well, what if it is not within tolerance? Well, then we hammer a little more, and then we measure 12 times to be on the safe side. And he said, okay, look at this. This is a pipe that has constant diameter from 3 sides, but it is not circular. And they said, well, we see it with the naked eye. It's not circular. And he said, yes, but look, your booster rocket has 3.5 meters in diameter. The O-ring is about this thick. If you deviate from a perfect circle by this much, the O-ring cannot accommodate the difference. there is a gap. Something will come through. And you do not see with the naked eye that it is out of shape. And you cannot measure it because there are these sets of constant width. Don't you know? And they did not know. So what I'm trying to say is convex geometry can sometimes be of vital importance. And it is foolish to think that we do not need solid mathematical education anymore because the computers can calculate everything. Now, if you want, you may come and try this little experiment later. By rolling these balls on the table, and the board does not go up and down, and I skipped the video that shows this. And I'm doing this experiment sometimes with a real person. Then we have these things. And the last picture that I want to show you is there are many three-dimensional bodies of constant width, and some of them are displayed in a museum of inventions in Paris. And when you go there, you should not go to the mathematics section. You should go to the section Eureka of the museum. Yes, Eureka. Okay. Now, in putting this talk together, I had some help from some people. First one was my former assistant, Jerzy Horak, who showed me how to download videos from the internet and how to incorporate them. Then I had some people that manufactured these bodies, and this is a friend from a steel company who manufactured this one. And last but not least, I want to thank you for your attention.
Yes. Theoretically, it's possible to use these bodies to make friction bearing.
Yes, it is possible. Yes, yeah.
Is it done, actually?
No, it has never been done. Well, manufacturing these things is maybe more expensive than manufacturing balls. This may be the reason. Yes.
Well,
yeah.
If they are from some expensive material, maybe the cost would be.
Yes. Yeah, but I do not know of any attempt to do it. Yes.
I have more theoretical question.
Yes.
You showed that one of Meissner bodies
Yes.
can be obtained by this procedure.
Yes.
The second one not.
Cannot be obtained. Yes. So the sets of bodies that can be obtained. I mean, so this mapping is not surjective. Yes. Yeah. This construction is.
Yeah. Though they have
the same volume. Yes.
The same volume. It's
Yeah.
very interesting.
Yeah.
And the conjecture is still open.
The conjecture is still open. Yes. Yeah.
And there are just two Meissner bodies that give
Yes.
the known minimum.
Yes.
Interesting. Yeah.
So.
It's always strange that two, because if it is one, it is more or less easy.
Yeah.
If the infinite number,
It may also be easy.
yeah. But if you have only two,
Yeah.
it's quite strange.
Well, I tried for a number of years to solve this problem because so far it had only interested geometers, and I was hoping that maybe as an analyst we are familiar with minimizing functionals under side constraints and so on. Maybe we have a chance. But in this case I did not get any farther.